You know, usually when we talk about learning a new language, the motivation is, well, it's pretty social.
Right.
You want to order a coffee in Rome, maybe haggle for a rug in Marrakesh. You want to connect with people. But today, we're looking at a language for a totally different kind of conversation.
A very different conversation.
Yeah, we're not trying to talk to humans. We're trying to talk to data.
It's a crucial distinction because, I mean, human language is just messy. It's full of slang, sarcasm, ambiguity.
Huh.
If I say, yeah, right to you, you know I actually mean no.
Mm-hmm.
Data doesn't get sarcasm.
No, not at all.
To talk to data, you need a language that is rigorously, almost painfully logical.
And that language is R. It's just a single letter, but it is this massive powerhouse in the world of statistics and data science.
Oh.
So we're doing a deep dive today into a guide called A Foundational Introduction to the R Language.
Mm-hmm.
And honestly, looking through this, R feels less like a coding language and more like a philosophy of truth-seeking.
That is not an accident. R isn't just a tool for, calculating sums. It's a direct descendant of the S language, which was developed at Bell Labs.
Bell Labs, that's a legendary research center, right?
Right.
Where they invented the transistor and the laser.
Very same. But here's the key context the source highlights. S, and by extension R, wasn't written by computer scientists trying to build software.
Oh, interesting.
It was written by statisticians who wanted to explore data. And that DNA, it affects everything we're going to talk about. It's why R feels so weird to programmers coming from, say, Python or C.
So it wasn't built for development.
It was built for exploration.
So our mission today is to decode that DNA. We want to take you from that intimidating blinking cursor to actually understanding the logic of how to manipulate lists, splice data frames, and avoid all the specific traps that R sets for you.
And there are definitely traps.
Oh, we'll get to the traps, but let's start with just the environment. You open R, it's stark, it's usually just a console window, and you see a symbol, a greater than sign.
The prompt, that's R just waiting for instructions. It's passive. It won't do a thing until you speak to it.
But the source makes a really big deal about a different symbol, the plus sign. And I think every beginner has a traumatic memory of the plus sign.
Oh, the continuation prompt, yes. So let's say you're typing a command. Maybe you're asking for the average of a list of numbers. You type the function, you open the bracket, you type the numbers, and then you hit enter.
But you forgot to close the bracket.
Exactly.
And R doesn't give you an error, it just gives you a plus I.
It's politely saying and. It knows the sentence isn't finished. But if you don't know that, you just keep hitting enter, getting more and more plus signs, thinking you've broken the entire machine.
It's a rite of passage. But this brings up a point the source really hammers home. You cannot learn R by just reading. You have to type.
It calls it the discipline of exactness. When you read code in a book, your brain, it just autocorrects.
Right.
You don't see the missing comma or the mismatched parenthesis. When you type, the error message screams at you.
Yeah.
You have to feel that frustration to learn the grammar.
It's muscle memory. So let's talk about memory in the computer sense. When we type these commands, where do they go? Do they just vanish?
Not if you're careful. R has a specific way of handling your session. It creates a workspace image called R data. That's where all your variables, your tables, your results, that's where they live.
Okay.
If you save that workspace, you can come back a week later, reload it, and it's like you never left.
And it remembers what you said, too.
Right, the .history file. It records every single command. This is actually huge for reproducibility. If you find some weird pattern in your data,
Yeah.
you have to be able to prove how you found it.
The history file is your paper trail.
Exactly.
Okay, before we get into the math, we need to equip ourselves. R comes with a base kit, but the real power is in the packages. The source uses one called Languager for its examples.
Think of R as a smartphone. It comes with a calculator and a clock. That's base R. But if you want to check your email or play a game, you need to download apps. Those are the packages. You use install.packages to download it once.
But just downloading it isn't enough, is it?
No. And this is a classic gotcha. You have the app on your phone, but it's not running. You have to open it. In R, you use the library command to load the package into your active session.
You have to do that every single time you restart R.
Every single time.
So install once, library every time. The source gives a pro tip here about an R profile file.
Yes. If you find yourself loading the same 5 tools every morning, you can write a little script in a hidden file called R profile. R just runs this automatically when it starts up.
Like setting your coffee maker on a timer.
Exactly. You sit down, and your tools are already on the workbench.
Okay, we're set up. We have our prompts. Let's do some math. At its most basic level, R is a glorified calculator. You type 1 plus 1.
And you get 2. But you have to pay attention to the output. It doesn't just say 2, it says 1, 2.
The bracket 1. Why? I mean, 2 is just a number. Why does it need an index?
Because to R, there's really no such thing as a single number. There are only vectors, lists. And even if that list is only one item long, R treats it as a vector of length 1. That 1 is just telling you, this is the first item in your result.
That seems incredibly pedantic.
It is, but it's consistent. R is built to handle massive streams of data. It assumes everything is a stream, even if it's just a trickle.
Speaking of streams, let's talk about how we save things. In almost every other language, if I want to set x equal to 5, I type x equals 5. R allows that, but it seems to look down on it. It wants arrows.
The assignment operator.
Yeah.
It's a less than sign and a hyphen, x -9 5. It visually represents the value 5 being inserted into the variable x.
It's a bit retro, like old flowcharts.
Well, it distinguishes assignment from equality. The equal sign, equal sign, is often used inside functions to set parameters. The arrow, x equality, is strictly for creating variables. It keeps the logic clean.
Okay.
But the source points out a feature that I honestly think is unique to R, the right arrow.
I laughed when I saw that. It's for people who plan poorly, isn't it?
Or for people who think fast. Imagine you're deek in some calculation. You type 2 plus 2, then divide by 7, then take the square root. You've typed this long, complex line.
And then at the end, you realize, shoot, I need to save this.
Yes. In another language, you'd have to go all the way back to the start and type x.
Yeah.
In R, you just stay at the end of the line, type x, and hit enter. It takes everything you just calculated and shoots it to the right, into x. It's a, oh, by the way, save this operator.
I love that. It acknowledges that coding is a stream of consciousness. Okay, let's step up from single numbers. The real meat of this guide is about data frames. The source introduces a data set called verbs,
This is a classic linguistic data set. It comes from a study on something called dative alternation.
which sounds incredibly academic, but bear with us.
It's actually something you do constantly. If I hand you a book, I can describe that in 2 ways. I could say, I gave the host the book,
Okay.
or I can say, I gave the book to the host.
Right. I gave the host the book is the noun phrase structure. I gave the book to the host is the prepositional phrase structure.
Exactly. And the question the researchers asked was, is it random, or are there rules governing which one we pick?
So they analyzed a ton of sentences and recorded all these variables.
Right. And now we have a table, a data frame. It looks like Excel, but it acts like a matrix. And here's the first culture shock for programmers. If I want the first item in this table, the index number is what?
Well, in Python or C, you start at 0.
But in R, you start at 1. The first row is row 1.
I can hear the computer scientists screaming.
It's a battle line. But for statisticians and, normal humans, counting starts at 1. It makes R more intuitive for non-coders.
Yeah.
Now, to get data out of this grid, we need coordinates. R uses square brackets, verbs row, column.
So verbs 1, 5 is the cell at row 1, column 5. Easy enough.
But the real power comes when you leave a blank.
A blank.
If you type verbs 1, so row 1, comma, nothing, interprets nothing as everything. It gives you the entire first row.
And if I flip it, verbs 1, 5.
Then you get every single row, but just for column 5. It's a slicing mechanism, horizontal strips, vertical strips. Just by leaving a blank, it's incredibly fast.
That is slick. But the source mentions that sometimes the data in those columns needs fixing. Like the length of theme column isn't just a word count, it's a logarithm.
Right. Statisticians love logs. They normalize data. But they're hard for us to read. So you can transform the column on the fly. You wrap the column name in the xpick function to reverse the math.
And R just does the whole column at once.
The whole column. You don't loop through the rows. You just say, take this column, apply this math, and it updates the whole vector instantly.
That's that vector thinking again. But speaking of vectors, we need to talk about the C function. C stands for combine.
Concatenate or combine, yeah. If you want to make a list manually, you type C, 1, 2, 3, 4. That creates a vector. It's the glue of R.
Okay, here's where we hit the danger zone. The source has a section on factors, and it warns that this is where beginners get crushed. What is a factor and why is it a trap?
Okay. Imagine you have a column for animacy. Whether the recipient is animate, like a person, or inanimate, like a library. To you, that just looks like text.
Right, words.
R sees it differently. When R loads that column, it converts it into a factor. Under the hood, R assigns a number to each category. Animate becomes 1. Inanimate becomes 2. It stores the integers and keeps a separate lookup table of the labels.
So it looks like text, but it acts like a number.
Precisely. It does this for statistical efficiency. But here's the trap. Let's say you filter your data. You decide, I only care about people. So you delete all the rows where the recipient is inanimate.
Okay, they're gone.
The rows are gone. But the factor definition remains. The lookup table still knows that inanimate is a valid category. It just has 0 entries now.
So if you try to make a bar chart,
R will draw an empty space for inanimate.
just like a ghost.
It's a ghost level.
Yeah.
And it will absolutely break your models if you aren't expecting it. You have to explicitly tell R to drop unused levels or convert the data back to plain text with as.character.
That is a crucial warning. Assuming a factor is just text will hurt you.
It will.
Let's talk logic. We want to ask questions. Show me all the sentences where the theme is animate.
We use logical operators. The double equals sign is the question mark. Animacy equals animate.
And we can combine them. The ampersand for A and D, the vertical bar for OR.
Right. Show me animathenes and D length greater than 5. This creates a logical vector. It's a long list of trues and falses that overlays your data frame, and R uses it to filter out the rows you don't want.
Okay, so once we have the data we want, we usually want to sort it. And the source makes a really subtle distinction here between sort and order. I always get these mixed up.
Everyone does. Think of it this way. Sort is simple. If you have a list of numbers 10, 5, 20, and you sort it, R gives you 5, 10, 20. It rearranges the content itself.
That seems fine. Why do we need order?
Because data frames are connected. If you just sort one column, you break the relationship with all the other columns. You've just scrambled the rows.
Well,
You don't want to shuffle the values. You want to know the new order for the rows.
so order gives me the match.
Exactly. Order doesn't return the data. It returns the indices. It says row 2 goes first, then row 1, then row 3. You take that list of instructions and apply it to the whole data frame, and the table rearranges itself safely.
That's a great analogy. Sort and shuffles the deck. Order writes down the sequence to shuffle the deck.
Perfect.
So we've wrangled, filtered, sorted. Now we want the truth. We want to analyze the patterns in the verbs data. The source introduces xtabs.
Cross-tabulation. This is the bread and butter of categorical analysis. The syntax here introduces the tilde.
The little squiggly line.
In R, the tilde means is modeled by or depends on.
So if I type xtabs, realization of rec plus animacy of rec, what am I asking?
You're asking for a frequency count of the interaction between those two variables. How many times did an animate recipient get a noun phrase? How many times did an inanimate one get a prepositional phrase?
And what did the data show?
It confirmed our intuition. Animate recipients, people strongly prefer the noun phrase. Give John the book.
We like to put people close to the verb.
Yes. And inanimate recipients, places or things, get pushed to the end of the sentence in a prepositional phrase. Give the book to the library.
So R proved that we play favorites with humans.
Statistically, yes. And you can verify the strength of that with prop.table, which turns those counts into percentages.
But what if you want to get fancier? With continuous data like word length.
Then you use tapply.
Tapply is one of those functions that makes you look like a wizard.
It's the split-apply combine strategy in one line. You want to know the average word length, but broken down by animate versus inanimate? You feed tapply 3 things. The data, which is word length, the grouper, which is animacy, and the function you want to apply, mean.
And it does it.
It splits the data into piles based on the grouper, calculates the mean for each pile, and then combines it back into a nice little table. No loops, no manual filtering, one line.
That is efficiency. Okay, final challenge. The source moves to a second dataset called head.
This is a study on Dutch neologisms.
Made up words.
Specifically, words ending in the suffix head. It's like avidness in English. Darkness, happiness. They took a root word, added head, and measured how fast people could read it. Reaction time.
But the data structure here is different. It's messy.
It's long. You have multiple subjects reading the same word, so the word basal hide appears dozens of times, once for each person who read it.
So if we want to know if the word itself is hard to read, we can't use the raw data.
No, there's too much noise from individual people being fast or slow. We need to average them.
We need to aggregate.
Exactly. We use the aggregate
That's
function.
good.
Very similar to tablet. We tell, take the reaction time, group it by the word, and give me the mean.
Boom. 1 row per word with an average reaction time, but we aren't done. There's a second table, right? A list of base frequencies.
Right. This second table tells us how common the root word is in normal Dutch. So we have 2 separate tables. One has reaction times, one has frequencies. We need to join them.
And this is where R behaves like a database.
The merge function. It's exactly like a SQL join. You tell R, look at table A and table B. They both have a column called word. Stitch them together where the words match.
And the result. Does the frequency of the root affect the reading speed?
It does. A clear correlation. If the root word is common, your brain recognizes it faster, even when it's stuck inside a made-up word.
So R, let us take thousands of messy reaction times, collapse them, merge them with external data, and find a real cognitive pattern.
All without scrolling through a 10,000-row spreadsheet. That's the power of the language.
So we've covered the syntax, the arrows, the traps, the analysis, but I want to zoom out. Why does this all matter? Why should someone struggling with Excel care about vectors and tildes?
Well, the source puts it beautifully. It says that the grammar of the S language in R is designed to guide you towards the appropriate way of thinking about your data.
That's a heavy statement. It's not just a tool.
No, it's a mindset.
Yeah.
When you work in Excel, you often stare at individual cells. You fix typos. It's very manual.
Sure.
When you work in R, you stop thinking about cells and start thinking about structures. You think in vectors, distributions, factors.
You're forced to treat the data as a whole entity.
Exactly. The code forces you to be logical. If your logic is flawed, the code won't run. It imposes a discipline that actually makes you a better thinker, not just a better calculator. You start asking, what is the underlying distribution? Are these categories real, or are they just ghosts?
So learning R isn't just about getting the right answer. It's about learning to ask the question the right way.
That is the ultimate takeaway.
I think that's a fantastic place to leave it.
Yeah.
So here's our challenge to you. Don't just let this wash over you. If you have a computer, install R. Open that console. Get that prompt. Type 1
Yep.
plus 2.
And when you see an error message,
Yep.
and you don't panic, it's just R asking you to be more precise.
Start your own hitter history. Thanks for diving deep with us today. We'll see you in the next data set.